My name is Bueno. I'm part of the ISORA organization. Before Professor Juan Enrique's talk, I want to present Professor Felix Escalante, which is the director of INCA, okay, for some words, okay.
Buenos días a todos. Gracias por su asistencia. Para mí es un honor darles la bienvenida para esta 11ª versión del Seminario Internacional de Optimización Matemática. Esta vez, este evento es muy especial para nosotros, en particular, porque es un evento en honor a nuestro gran amigo, y yo creo que entre muchos de ustedes, Jean-Pierre Poussin. Este evento es en honor a su aniversario, ¿no? Y evidentemente estamos felices por esta razón. Además, quiero agradecer también a las instituciones que nos han apoyado para la realización de este evento, ¿no? No lo puedo mencionar por ahora, creo que debemos empezar ya. Y bueno, les deseo una buena estadía aquí en Lima. Gracias.
Good morning, everyone. So we will begin with Juan Enrique Martinez-Legaz, who is a good friend of us. So I'm really happy to present him. He will talk about integration of Fenchel to the Fenchel version analysis.
Thank you. Good morning. Well, I think I'm not revealing a very deep personal secret if I tell you that it's a pleasure for me to come to Peru, because I have come already 9 times. On 7 occasions to participate in this ISORA meeting, which I like so much. And so it's really a great pleasure for me to be here again. And this year even more, because it's to celebrate Jean-Pierre's birthday. Jean-Pierre is such a good friend of mine, and he's one of the mathematicians I most admire. And I'm not saying this because he's here or because this is a special occasion. So many of my friends know, because before this, on private conversations, I told them that really I admire his work very much, and which has been very, very influential in my own research. So happy birthday, Jean-Pierre. And so I'm going to talk on a very classical topic in convex analysis, namely the integrations of Fenchel subdifferential. It has an old story which starts with the classical formula by Rockefeller, which everybody knows, dates back to 1966. So this formula tells us how to integrate the Fenchel subdifferential. If you know the subdifferential mapping, then you can recover the function by means of this formula up to an additive constant. So you are free to choose f of x0, but then after you make this choice, then taking this supremum, which is over points in the graph of the subdifferential mapping, then you recover the function. Well, but there are also much more recent contributions to this topic. There have been extensions to non-convex functions. If I have time, at the end of my talk, I will tell you a short history of what I know about the integration of Fenchel subdifferentials. But what I'm going to do here is something very simple, maybe too simple, which is, I'm not going to consider non-convex functions, just convex functions. And for the ease of presentation, I will just work for functions defined on Rn, although at the end of the talk I will mention also extensions to locally convex spaces. And So I will present a formula which is simpler than this one, stronger than this one, which has a number of consequences, and which is, in my opinion, more interesting, is that it has a very easy proof. There is only one idea in this talk, which will come in the next slide, the next page. And unfortunately, it is not my idea. It is a very simple idea produced by a young Czech student, Kocourek. He was a young master student in National Sun Yat-sen University in Kaohsiung, Taiwan, 5 years ago. And now he is a PhD student. He's starting his third year in the doctorate studies at NYU, New York University. And he produced the following idea for a result which I will mention later as a consequence of my result. The idea is extremely simple. I needed almost 5 years to realize that his idea can be used to produce the integration formula I am going to present soon. This is the only idea of the paper, and is an idea due to Kocourek. So, you consider a point in the relative interior of the domain just to make sure that there are subgradients. Then you take a point in the domain of F, and then you make a subdivision of the segment with endpoints x0 and x. Then consider a selection, single-valued selection of the subdifferential mapping on the relative interior of the domain. Okay? And then, so at this point in the subdivision, you take a subgradient using this selection, and then you write the subgradient inequality. Okay? And then you add up all these inequalities. On the left-hand side, you have a telescopic sum, and this is what you get when you add the right-hand sides. So you get this inequality. Then you do exactly this, first of all, then now you take the lim sup, and you end up with this inequality. Once you have done this, you proceed exactly in the same way, but backwards. Okay, here you were taking a subgradient at a point, and then you consider the next point in the subdivision. Here you do the same, but then the preceding point. And then you do as before. You make the sum, and take the lim sup. And then you get this inequality. If you put together this inequality with this inequality, then you get the formula I am presenting you now. So this is an integration formula. You use subgradients, and by means of the subgradients, you obtain an expression for the function. The function f of x is equal to f of x0 plus this limit, or plus the supremum. It can be easily proved. So, first of all, you have a limit, which in Rockefeller formula it was not a limit, it was just a supremum, but you also have a supremum if you prefer. And you don't need to know all the subdifferential mapping, just a selection, a single valued selection. And Rockefeller formula follows as a corollary from this formula, because it's easy to see that the expressions here occur in Rockefeller's formula, are particular cases of the elements in Rockefeller formula. So when you take the supremum of over a subset, you get f of x minus f of x0, so you will have the same consequence when you take the supremum over a larger set, because one inequality is obvious. Okay, so this formula is stronger, is simpler, and it has a number of consequences. One of them is the original result by Kocourek, where he proved that if two convex functions have a subdifferential with non-empty intersection everywhere, then they are the same up to an additive constant. The classical result is with equality. Here you only need non-empty intersection. In fact, this result also can be proved from a Rockefeller result using that. If there is a non-empty intersection everywhere, In particular, there is an unempty intersection at differentiability points, which means equality. Okay? Then these two functions, if they have an unempty intersection of the subdifferentials everywhere, must have the same gradient at differentiability points. And the set of points, of differentiability points, is a full measure. Moreover, at other points, you recover the subgradients by taking limits of gradients at neighboring points. So the gradient determines the subgradients. Then putting all these things together, it follows that if there is no intersection, there is equality. So it's the same. But to produce this result from Rockefeller formula, you have first to prove Rockefeller formula, which is not trivial to prove. The original proof, I mean. Then you have to use that differentiability points, the subdifferential reduces to the singleton of the gradient. Then you have to use that convex functions are local ellipses. To use Rademacher theorem saying that local ellipses functions are differentiable almost everywhere in the sense of the Lebesgue measure. So you have to use a lot of things to end up with the conclusion that if you have non-empty intersection, then you have equality. Using that idea by Kotzouret, you have a very elementary, purely algebraic proof of the same result. So I think it was his very brilliant idea. Well, now I'm going to draw some consequences of this formula. First of all is the uniqueness part in this theorem, this corollaries. The second corollary is classical, well known by Rockefeller, says that the maximal cyclically monotone operator is the subdifferential of a uniquely determined up to an additive constant lower semi-continuous convex function. The preceding corollary is more general because it says that the uniqueness, for the uniqueness, you only need the domain to have a convex relative interior. Then Rockefeller results follows from these more general results because it is well known that subdifferentials have a convex, have a domain whose relative interior is convex. Okay, and another consequence which can be easily drawn from all this is that if you have a cyclically monotone operator with a domain which is convex and relatively open, it may have many maximal cyclically monotone extensions, but all of them would agree on the domain. This is the same result as before, the fundamental formula, but using directional derivatives. This is another advantage of this formula over Rockefeller's formula because since here you only need a selection of the subdifferential mapping, you can choose the selection so that you get the directional derivatives. Okay, so you have here an integration formula in terms of one-sided directional derivatives. And now I'm going to analyze some issues about is the supremum or the infimum attained and such things. Well, they are not attained except, they can be attained only if the restriction of the function to the segment within points, the 2 points we are considering, x0 and x, is polyhedral, meaning piecewise affine. In particular, this follows that if the function is strictly convex, these suprema or infima are never attained. Also, how is the convergence of those sequences to the limit f of x equal to f of x0? Well, these sequences need not be monotone. But you have here an example showing that this is the case. Just take the absolute value function x0 equal to -1, x equal to 1, and consider the selection of the subdifferential mapping which takes the value 1 at the origin. This is the only choice we need to make because everywhere else is determined because it's differentiable. then it's a very easy computation to show that these two sequences, one can do the same for the last one, so that these two sequences in this case reduce to this, which is a non-monotone sequence. But it's very easy to obtain monotone subsequences out of these sequences. To do this, you only have to make the composition of those sequences with an increasing sequence of positive integer numbers with the property that each term is a multiple of the preceding one. In other words, I mean, in these formulas you are making subdivisions of the segment x0x. Then what you need is the next subdivision to be a subdivision of the preceding subdivision. And this will be the case if nk plus 1 is a multiple of nk. Well, the next topic I'm going to consider is a characterization of epsilon subgradients in terms of subgradients. This is a topic I studied with Michel many years ago. We published a paper in which we exploited Rockefeller formula to characterize epsilon subgradients in terms of subgradients. The idea is the following. The subgradients determine the function up to an additive constant, and the function determines its epsilon subdifferential. Even if they differ on an additive constant, there is no difference with the epsilon subdifferential. Then the subdifferential determines the epsilon subdifferential. But how to express directly the epsilon subdifferential in terms of the subdifferential without going through the convex function? And we produced our result. Now it's obvious that we have such a possibility with the new integration formula. And this is what we get now. Then a point xx star belongs to the graph of the epsilon subdifferential if it is monotonically related up to epsilon with all points of the type x0 in the relative interior of the domain of the function, and the second component of the pair is this average of subgradients taken in the interval x0x. Some consequences of this theorem are, well, first this one, in which I repeat the result by considering directional derivatives, thanks to the fact that we only need a selection, so we can take the selection of the subdifferential which yields the directional derivatives. And observe that in these results, epsilon is non-negative, so it can be equal to 0. So then we would be characterizing subgradients in terms of subgradients. In other words, we are obtaining a maximality result for ordinary subdifferentials different from the classical one. This is what we get. If we have a Laguerre semi-continuous proper convex function, then its subdifferential is maximal in the set of mappings that have a nearly convex domain. Nearly convex means that a set is nearly convex when it contains the relative interior of its convex hull, or equivalently, if it is contained in the closure of one of its convex subsets. Okay, so the subdifferentials are maximal in the sets of operators which have a nearly convex domain and a single-valued selection on their domain with this property. The property that the point is monotonically related to every point of the time of the type I mentioned in the preceding corollary. This condition, this monotonicity property is, let's say, intermediate between ordinary monotonicity, which will occur in the case n equal to 1, and cyclic monotonicity. This is a particular case of cyclic monotonicity. Well, in the last part of my talk, I will consider extensions to locally convex spaces in which, since we don't have a nice result, at least that I know, on non-emptiness of the subdifferential, then I will consider epsilon subdifferentials, which are non-empty if we are dealing with lower semi-continuous convex functions. proper convex functions. So, and this is the result. What we need here is to consider a selection of the epsilon subdifferential mapping. So Sx epsilon means a subgradient of f, epsilon subgradient of f at x. And then if we take the sequence epsilon m in such a way that it converges to 0 faster than 1 over m, then we get this integration formula in terms of this selection of the epsilon subdifferential mapping with limits, or with supremum. In case we write a supremum, we need the epsilon sub in the formula. And as a corollary, we have this formula, which is reminiscent of Rockefeller formula, but with epsilon subgradients, and you have this extra term here. And this is also related to a formula obtained recently by Rafael Correa, Yvonne Garcia, and Abderrahim Hantut. This is similar. And another consequence we get from this result is a result we already got together with Regina Burachik and Marco Rocco, which says that if we have two lower semi-continuous convex functions with a common domain, with the property that at every point in the domain, and for every epsilon, the epsilon subdifferentials intersect, then the two functions are the same up to an additive constant. Well, this is the last result I'm going to present, and I will finish with telling you a little bit of the history of this topic and mentioning some of the references. So this is the starting point, Rockefeller formula. There is an alternative interesting formula by Verona and Verona. Then Bachir, Aristanelidis, and Jean-Paul Penot, I think they were the first to consider non-convex functions, integrations of non-convex functions. And they consider, what they proved is that if you apply Rockefeller formula to a non-convex function, if the function is one coercive, then what you integrate is actually the second Fenchel conjugate of the function. In the next paper, the main contribution is to relax the one coercivity condition to epipointedness. And in this third contribution by Aris and his co-authors is that in that formula you can restrict to points x in the domain such that the corresponding point in the graph is an exposed point, strongly exposed point of the epigraph of the function. Then this is the paper I mentioned in which Rafael Correa, Yvonne, and Abderrahim Hantut, they consider integration of non-convex functions but using epsilon subdifferentials, again for epipointed function. And Marco Lopez and Michel Boll produced a variant of this formula in which is more complicated, but they remove the epipointedness assumption. Well, this is the result which contains the only idea in my talk, this proof. And we exploited already his idea, together with Abderrahim, to characterize Lipschitz DC functions. This is the paper, joint paper with Michel, in which we characterized epsilon subdifferentials in terms of subdifferentials. And this is the last paper I mentioned, in which we proved that, among many other things, that if the epsilon subdifferentials intersect everywhere and for every epsilon, then the two functions are equal up to an additive constant. And this is all I wanted to tell you. Thank you very much for your attention.
The first result you mentioned, you're in a RL, you take points in the red interior of the domain, right? So the Rockefeller solver is in any kind of space.
In any?
In any kind of space. In any
Well,
space. Yeah.
mhm.
And then
Well,
say for instance that you gave the first corollary, and then this relative interior disappears. And in the one that you use direction derivatives. The first one that you use here, right?
No, x0 is as in theorem 1. So x0 is in the relative interior,
Okay. As before.
as before. No, I mean, I'm sure there are possible extensions to infinite dimensional Banach spaces. But, I mean, just for simplicity, I made this presentation here, and I'm not interested in such general, at this moment. Okay, so I just wanted to present how this simple idea by Kotzurek can be used to obtain the integration formula by Rockefeller, but even something stronger and easier in an absolutely elementary way, using nothing, just the definition of subgradient. That's the brilliant idea by Kotzurek.
Just a very simple question. Everything of this is based on selections. So
Yeah.
it's taken a selection from this, and nothing is asked to this selection. So it sounds to me like a kind of, I mean, the only thing that is needed is it is single valued point.
You only need to know one subgradient at every point.
Yeah.
That's it.
So it sounds like representation theorem of class of monotone operator, because you have a single value map. It represents the class, and with this you will construct everything, right?
Yes.
So,
Yes.
so this could sound as a way to how to say to reduce the knowledge of the monotone by simply having this kind of.
Yeah, that's true. You are right. You just need to know one subgradient at every point, then you know everything.
Yeah.
Mhm.
So, thank you.